Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, part 2, what is deep learning? In part 1, we talked about what is the difference between econometric, machine learning, and deep learning. And we said that depending on different type of the data, what's the structure of the data, if the data is structured or not, we may end up using econometrics or machine learning or deep learning. Okay. However, in this video, I will talk about what is deep learning in general at the very high level compared with AI and machine learning. And then we're going to have a conversation about what is the difference between machine learning and deep learning in details. We know that both of these models are used when we are interested in predictability power of the model, but which one is working better at what situation? So let's look into that. So this is our neural network. Let me use my pen. I want you to think of a neural network as a black box. So it's very simple. At the very first layer, we have a bunch of inputs. So these are our features. It can be anything. It can be age, education, gender, and etc. And we pass these features to a model, and then model does something to that, and it's going to generate some outputs, right? So the output, in this example, this is a classification output. So the output is going to be class A, class B, class C. You can think of it in stock market, you can think of it as, I don't know, buy, sell, hold. Or if it is image recognition, you can think of it as, I don't know, different dog, horse, cat, right? So this is at the very naively speaking what's going on, right? So give some inputs, do something to it, and then generate some outputs, right? Now let's look into the details. So remember, this is part of module 1, which was the introduction to deep learning. All right, so you may have seen something like this, that deep learning is a subset of machine learning and machine learning is a subset of AI, artificial intelligence. But let's break it down and see what do we mean by that. So I would like to start by the definition of intelligence. So intelligence is this ability to process information and make decisions based on that. Now, if this intelligence is a biological inspiration, as in humans, we call it human intelligence. But if this intelligence is engineered and done by machines, we're going to call it artificial intelligence, right? So artificial intelligence is any technique, let me use my pen, it's any technique which enables machines to mimic human behavior. So as you can guess, this is a difficult task. You know, the theory was, actually, it's nothing new. It was around since 1950s. But the computation power was not there yet, so we had to start from somewhere. So we started back in 80s, we started with setting the scene for the computers. We said that, you know what, let's go ahead and these are the rules of the games. We set some rules, we set some designed some algorithms, and based on that, the machine was able to learn from the data. Okay, so this is what we call machine learning. So machine learning is a subset of AI that enables computers to learn from data, and the model is trained. The key term is this, train. I want you to pay attention to that. The model is trained with a set of algorithms. So we, the humans, are the one who set the rules and say that, hey, this is the algorithm, use that, apply it to the data, and then make some predictions, right? And then the next one is deep learning. So it was in 2010 that the computation power was there and the algorithm was there. And the deep learning is a subset of AI that extract patterns. So here the key term is extracting patterns from the data using neural networks, right? We're going to talk about the details of the neural networks, but the key point here is that we are not engineering some features like in machine learning. In machine learning, we the humans are going to set the rules, come up with some algorithms, and most importantly, we're going to engineer some features, right? The feature engineering is done manually. However, in deep learning, the entire goal is to extract these patterns, these features from the data automatically. So that's a main difference between deep learning and machine learning. And the thing is that once these patterns and features are extracted, we can pass this to a machine learning model, and the machine learning model can come up with some basic predictions, right? So that's why we say deep learning is a subset of machine learning, because when the data set is unstructured, we need to extract those patterns automatically, because hand engineering those patterns is difficult. And then once we're done with that part, we're going to pass it to a machine learning model, and the machine learning model is going to make the predictions. Okay, so that's the difference between AI, ML, and deep learning. Okay then, so what is deep learning? Deep learning is a type of machine learning that uses multiple layers of neurons. So what do we mean by neurons? So this is a neuron, this is a neuron, these are all neurons, right? Okay. And we have some inputs and outputs. Okay, so this is a very simple example of neural networks, right? There are multiple layers. So this is our layer number 1, layer number 2, and we have an input layer and an output layer. Don't worry about the details. I will cover these things in module 4 in very detail. So don't worry about it now. For now, just try to understand it at a very high level. So we have multiple layers of neurons that are going to process data, and then based on that, we are going to make some predictions, right? So this neuron is going to get some information from input layer, let's say these 3, and then do something to that. We're going to talk about all these things. What is that something? And then make some output and pass this information to the next layer. And the next layer is going to pass the information to the next layer and goes on, depending on how many layers do we have. At the very end, let's say this is our last layer. It's going to pass some information to the output, okay? So this is how the processing of information is done. It's sequentially, right? By sequential, I mean it goes through the layers, right? But at once. So the goal of deep learning is to build a model that can automatically learn complex pattern. So the key term here is automatically. So this is what makes deep learning so powerful and, in my opinion, beautiful. So it can automatically learn complex pattern from the data and make accurate predictions. So let's see how it happens. So let me give you an example and I'll talk about this automatically thing, because in machine learning, this is hand engineered. In deep learning, it is done automatically. Okay, so let's say I have a very simple example. I want to come up with some predictions for a housing price model. So let's say we have some feature. This is our input level. The features are pretty straightforward. So imagine I want to predict the price of a house. What could be the 3 most important features? So maybe we have square feet. We have, I don't know, we have number of bedrooms. And let's say we can have a location, right? So these are the 3 features. And at the end of the day, remember, we want to do something to that. And at the end of the day, we want to come up with a prediction for the price of a house. So this is the output, right? So simple input with input layer with 3 features, square feet, number of bedrooms, and location, and output is just making some predictions for the price, right? If I want to do it using machine learning, what would I do? I would say, you know what? Let me give you some background. Imagine you want to say, okay, what is the relationship between square feet and price, number of bedrooms and price, and location and price? You might want to say, let's look at this square feet. So imagine this is your square feet, and this is the price of a house. You can confirm that the relationship between square feet and price of a house is not necessarily linear, right? So maybe if the square feet is increasing, the price increase, but at some point the speed is going to decrease. And even after some point, it's going to plateau, something like this, right? So because if the square feet keeps increasing, the price of a house is not going to increase at an increasing rate or even a linear rate. It's going to increase at a decreasing rate. So imagine you want to model something like this, right? So that's, again, as a machine learning engineer, you have to think about it. How can I do that, right? So you say, maybe I want to add square feet. Oops, sorry. I want to add square feet and square feet squared, square feet to the power of 3, and etc. to the model. Look at that. I'm engineering these features, right? The same story for number of bedrooms, the same story for location. And what about a combination of the two? So for example, what about a combination of square feet and location? What about a combination of square feet and number of bedrooms, right? So you can think of, or what about a combination of all of them? Square feet, bedroom, location. So as you can see, this part in machine learning is kind of an art. So you have to have a good domain knowledge to understand the relationship between the features and literally engineer these features, right? So that's the way to do it in the machine learning. But the beauty of deep learning is that this part, this mixing and matching the features, is done automatically. So that's where the term automatic is coming from. So the idea is that, say, okay, let's go ahead and mix these things with different kind of mixing, right? And pass it to the next layer, right? So this, for example, this neuron is a combination of all the 3 features. This neuron is also a combination of all the three features, and etc., etc. Then we're going to pass these mix to make another mix in the next layer, right? So as you can see, the relationship is going to become more and more and more complex, right? But the thing is that we have no idea what are these features. And the beauty of the deep learning is that it's going to automatically pick the features that has the most important impact on the prediction. Okay, so this is what makes deep learning very powerful. This engineering part is going to be done automatically now. Okay, so as I said, the beauty of neural network is that you're going to give it all the features, and it decides at, for example, at node 1, what feature was the most important one. So at the end of the day, it's going to say, you know what, at this node, maybe this was the most important one, then this, then this. At this node, maybe only this one was the important one. And then it goes on and on and on. So that's the difference. That's the main difference between deep learning and the machine learning. The feature extraction is done automatically. Okay, now depending on how do we put these layers together, we will come up with different networks, right? So here are some examples for the networks, and we already talked about this standard neural network. So this is a very basic standard neural networks. We have some input layers, output layers, and a bunch of layers in between. Okay, then we can come up with, so for example, what's called convolutional neural networks. So the input of the convolutional neural networks is usually images, right? So this means that we have to do some tricks, we have to use some operations, namely convolutional operations, to be able to use it and pass it to a simple or standard neural networks. So we're going to cover these ones in the deep computer vision part. Then in the deep sequence part, we will talk about another structure, another network, which is, so for example, here, this is a recurrent neural network. And recurrent neural network, you can think of it as each of these networks is a standard neural networks at a specific timeline, right? So for example, this is t is equal to 1, time is equal to 1, time is equal to 2, time is equal to 3, right? And we are simply rotating these standard neural networks in a vertical version and then stacking them together, right? So this is what's called sequential models, and I'm going to cover it in one of the modules that we cover, the deep sequence modeling. And then lastly, we will talk about transformers. For transformers, we start with, let's say, positional encoding the inputs. So we have to, again, do some tricks to the inputs, whatever they are. And then when we pass it to the next layers, we have to see at what part of the layer or neural network we should pay more attention, right? So we're going to use a attention mechanism and then make some predictions based on that. So this is what we're going to cover in the transformer section, okay? All right, now let's see how do these networks work in practice. Okay, so as you can see in this example, we have a neural network with an input layer and 2 hidden layers and an output layer. Okay, so let's start from the beginning. The network uses a series of interconnected layers, in this case 2 hidden layers, with each layer transforming the input and passing it to the next level, right? So let's look at this one. So for example, this layer, the neurons are transforming the data from the previous layer. So these are the inputs, and that transformation, we're going to talk about the details later on. We're going to apply something called activation function. How do we sum up those inputs and apply an activation function and generate an output? Okay, and then so this is how the data is passed through from layer 1 to the layer, in this case number 4, which is the output layer, right? Then the final layer of the network produces the output. So this is our final layer. This layer is going to generate the output. So we're going to use so for example, some special activation functions here to generate, if it is classification, 3-class classification, right? If it is regression, we're going to sum them up in a special fashion, right? So this output, whatever it is, it's going to be out compared to the true output label in the data, right? So look at that. I have a bunch of inputs, and this input is going to make a prediction. Let's call it y hat 1, y hat 2. So this is class 1, class 2, class 3. And imagine we are using some softmax function. I'm going to talk about the details later on. And these are some probabilities, right? And now I'm going to compare this output with what happened in reality, in real world, or in the train set. Now, if the output is, if what the model predicted is far from away from the reality, then we have to update the weights. And this is exactly what happens in the next step. So the network is then adjusted to minimize the difference between the predictions and the output and the true labels out there, right? This process is repeated until the network has learned to make accurate predictions, right? So later on, we're going to talk about backpropagation and see how these things are exactly done. But I want you to take it again, look at the very high level, what is being done here. I have an input. I pass the input to a bunch of layers, and there are some mathematical operation done at each layer, and then it's going to be passed to an output. I compare this output with y in reality, sorry, with an I don't know what's going on, with an actual y in reality. If the distance is too far, I have to go back and update these weights, right? So all these lines are connected to each other using some weights. So then the network is going to adjust those weights to make sure that the new output, the new y hats, are closer to the true label y, okay? So this is, in a nutshell, how deep learning networks work. Okay, now let's answer two very important questions. Why deep learning and why now? Okay, let's start with the why deep learning part. Okay, so in deep learning, pay very good attention. The model is not explicitly programmed with a set of rules or algorithm. It's unlike machine learning that we had to set the scene. Here, the models are not explicitly programmed. Instead, the models learn to recognize patterns and make predictions by adjusting the connections between the neurons, right, in different layers, right? So this is very, very important. And the second reason that why we are interested in using deep learning is that this is, in my opinion, even more important, that it can learn the underlying features directly from the data, okay, in a hierarchical manner. I'll talk about in a hierarchical manner in the next example, but I want you to pay attention that no feature extraction is required here. Again, it is unlike machine learning. So let me give you an example. So imagine we're doing some image classification. At the top, we are using machine learning. At the bottom, we are using deep learning, right? The input is an image. Let's say it's a color image. And in the computer vision, we're going to talk about what computers actually see. So what computers here actually see is a 200, let's say this is a 200 by 200 image, and because it is colored, it has 3 channels. So what computers see is something like this, you know, 3 200 by 200 matrices, basically some numbers, right? And now if I want to look at the input numbers, so the input is high, actually 200 multiplied by 200 multiplied by 3, what is it, 120,000? So we are talking about 120,000 features, right? So it's very, very high dimensional features. So right away, we know that maybe we have to do something about it. If I just pass this feature to a random forest or the simple decision tree, it's going to have a hard time because remember, this is super high dimensional data, and we're only talking about a low resolution picture like 200 by 200. Imagine you wanted to do something like 1024 by 1024. So easily the number of features is going to pass millions, right? So let's say, regardless, we're going to use machine learning, and the first thing we need to do is to reduce the dimensionality. We can apply some PCA, so for example, principal component analysis, to extract these features, right? So we can extract these features, let's say going from 120K dimensions to, I don't know, 100 dimensions, right? We can do it that way. We can do this by feature selection, something like applying penalized regression like lasso, which reduce the dimension of the data. But what we're doing is something, again, as I said, we have to do this manually. So this is a key term, manually. We're doing this feature extraction, feature selection, feature engineering manually. And then once we're done with that, we pass this lower dimensional data to a simple, in this example, decision tree. And that decision tree is going to come up with some classifications. Okay, this is the input, the output, is it a car or not car? Okay. So that's if you want to apply machine learning to an image classification problem. Okay. Now, the better solution is deep learning, because in deep learning, first of all, it can handle this high dimensional data, by applying the methods called convolution. Again, I'll talk about the details later on. But the more important thing is that this part, the feature extraction and classification, is done at the same time in the neural networks. And most importantly, it's done automatically. So this is what makes the deep learning very, very exciting and more appealing compared to machine learning when it comes to image recognition, right? So this feature extraction or engineering features is going to be done automatically. All right, now let me give you another example and explain what do I mean when I say that in deep learning, the features are going to be learned directly from the data and in a hierarchical manner. So let's talk about the details of that hierarchical manner. So imagine we have a picture here. This is our raw data. Let me use my, okay. And you want to figure out that, okay, this is a face. So imagine this is a face recognition problem, right? And if I know nothing about deep learning, how do I do that, right? So I would say, okay, let's start from a very basic level. At the very first level, you have to figure out how can I know that there are some edges in different part of the image, right? So I have to come up with some filters. We're going to properly define all these terms. So what is filter, what is convolution, and et cetera, later on. But just think of it in a very, very abstract way. So I can say, you know what, let me go ahead and engineer an edge, right? So what do I mean by that? So I'm going to say that, okay, imagine this is an edge, right? So this is another edge, this is another edge. So each of these edges are some filters. Basically, these are some simple matrix transformations, right? And now I can apply those edges throughout the image and figure out that, okay, for example, here is an edge, here is an edge, or I don't know, here is an edge, here is an edge, and et cetera, et cetera. And then in the next level, so this is where the term hierarchical is coming. In the next level, I can combine a bunch of these filters and then to look at it at the higher level. So maybe if I combine a bunch of these edges, I can say, okay, so this is maybe an eye. I can apply the same filters around here and I'll combine a bunch of them in the next layer, call this one an eye too, right? So, but the key thing is that this engineering the features is done manually. And as you can guess, hand engineering these features for unstructured data like images is almost impossible. Even if it is not impossible, it's hard to scale it in practice. It's not scalable, right? And maybe again, if I'm hand engineering these things, after detecting a bunch of edges, here I realize that, okay, maybe this is a mouth, right? This is a nose, and etc. And then at the very last layer, we're going to combine all these things and then call this, okay, it's a human, so it's a face. Okay. So this is, if you want to hand engineer these things, again, in practice, it's almost impossible. It's not scalable. Okay. Now, the beauty of deep learning is that it's going to do it for us automatically. I want you to pay very good attention that this process of extracting features, extracting these filters themselves is automatically done now, right? So this means that it's going to be super scalable. So at the very low level, so this is a low level feature extraction, the neural network is going to extract, let me show you this. It's going to extract some lines and edges, right? So let's say this is the first layer. We're going to extract some lines and edges. In the next layer, we're going to combine a bunch of these, let's say lines and edges, and look at the higher, from further away, and come up with some mid-level features, right? So maybe joining a bunch of these lines and edges is going to tell us, okay, this is eye, this is nose, and et cetera, right? So this is the mid-level features. And then in the next layer, we're going to combine those mid-level features to come up with some high-level features. So this is a face, this is a face, this is a face, right? So these are different facial structures, right? Now, again, remember, the goal in deep learning is to do these things automatically and extract the patterns, the complex patterns from the data. So this is your input. This is the output, which is basically, you can think of it as some extracted features. And then I can pass that extracted feature I don't know, depending on where we're looking at it, to a simple machine learning model to perform classification, right? At the very last layer, I can apply simple logistic regression for classification and things like that. Okay, so that's why deep learning is designed and structured for working with unstructured data, not machine learning, not econometric. Okay. All right, now let's put it all together and compare the machine learning and deep learning in a nice table. Remember, in part one, we looked at what is the difference between econometrics or statistical learning models versus machine learning / deep learning. Now we want to break it down. What is the difference between machine learning and deep learning in more details? Okay, so let's start by the focus. So in machine learning, the focus is just general purpose prediction. We know that machine learnings are good for making predictions, especially if the data is structured. So that's the main goal of using machine learning model. However, in deep learning, the goal or the focus is to extract those high-level features from the data. So remember that image recognition problem. It was super hard to do it with the machine learning. It was not scalable. It was almost impossible. But with deep learning, the goal was to extract those features. So the goal was not necessarily to make prediction. In deep learning, we extract those features, we pass it to a machine learning model, and the machine learning model is going to do the prediction part. Okay, I hope that's clear. Then we can look at the level of abstraction. In machine learning, we explicitly program the, let's say, the model, right? So the idea is that we're going to say, okay, here are the rules of the game, here are the algorithms. You go ahead and based on the performance of based on the performance metrics. So for example, what is the difference between actuals and predictions? Go ahead and update the model, right? The machine learning model, right? So the key term is that it is explicitly programmed. However, in deep learning, this updating the weights is the learning thing is done by adjusting the neurons, right? Again, don't worry about the details. I will cover them in module 4. Okay, then examples. What are some models, both from machine learning and deep learning? In machine learning, hopefully you have seen KNN, SVM, decision trees, random forests, boosting models like XGBoost. For deep learning, the ones that at least we cover in this course is we talk about CNN, RNN, LSTM, GAN, and transformers. So these are, don't worry about the names, we're going to cover them later on. So the other difference is, does this learning technique requires feature extraction or not? I think that you're in a good shape now, and you can realize that in machine learning, yes, feature extraction is required and it's done manually. But in deep learning, we don't need to do that. It's automated. Okay, and so for that reason, the processing power, the machine learning requires high processing power compared to the deep learning requires high processing power compared to the machine learning. Okay. And interpretability, both of them are not necessarily interpretable, but if one of them is more interpretable, that's a machine learning one. Because again, remember the dimensionality of the data, the level of abstraction, and etc. that's used in deep learning is a lot more complex compared to machine learning, right? So I would say interpretability for machine learning is medium to low, for deep learning is very low to almost none. Now, if you have neural networks with hundreds of different layers, and thousands and millions of neurons, so there's not much to interpret there. Execution time. So interestingly, the deep learning models takes a lot of time to train them, but once they're trained, they're a lot faster compared to machine learning models, right? So in a nutshell, so you can think of it as, because deep learning models, we have to give them a lot of data, and it takes the train time usually is longer compared to machine learning. But once the weights are estimated, once we know that what are the weights that it goes to each neuron, we're done. The testing part is a lot faster compared to the machine learning model. Now let's talk about, so this is the last slide, let's talk about why now, right? So here we have, on the horizontal axis, we have data size. On the vertical axis, we have model performance, right? So for model performance, if it is regression, you can think of MSE. For classification, you can think of accuracy, right? But the performance in the test set, or the cross-validated performance, right? So as you can see, let me actually bring the bullet points. In a small data set, if the data set is small, perhaps traditional machine learning, and even if the if the data is structured, even if something like econometrics, when the data set is small and low dimensional, traditional machine learning is more effective. And we have seen that in practice, traditional machine learning, when the data is small, outperforms the larger neural networks. So the red line is traditional machine learning algorithm. Then the orange one is a small neural network, the green one is medium neural network, and the blue one is large neural network. So let's compare the blue and the red one. So this is, as you can see up to here, if the data set is smaller than this amount, this threshold, then our red model is performing better, okay? So I want you to think of it as accuracy, for example. The higher, the better. But when we have more data, so it seems that the neural networks or the deep learning models are outperforming. Okay, the performance of the deep learning is better when the data is larger. So as you can see from this image, and but the problem is that the training of this large or super large neural networks is computationally expensive. Okay, but the good news is that today, we have that power. So today we do have the hardware. So now with the hardware and the amounts of data that we have available, more importantly, we can synthetically generate this data as well. We're going to learn these things later on, how to synthetically generate data and use it for training the model, right? So the hardware is there, the data is there. So why not using deep learning? Because we know that deep learning is going to outperform machine learning when we're here. Okay. And another reason that we can think of speeding up the training part is algorithms, right? So every couple of years, or even less than that, we come up with completely new version of the older algorithms that's going to speed up the entire process, right? So algorithms are playing an important role in speeding up the training process. So overall, it seems that, I don't know, as of 2023, deep learning, this is the right time to both learn the theory behind it and apply it, because we do have the computation power, we do have the data, and we have newer algorithms day after day. All right, so that was pretty much it. We wrapped up module 1. In the next one, I will talk about, before we jump into the details of these models that I just show you the laundry list, I will help you to set up your Python environments, because the deep learning environments, we are going to end up with working with multiple packages, and I want to make sure that when it comes to applied part of the course, we are all on the same page. Okay, until then, take care.